In the second week lecture, we're going to talk about the physics of sound. It's essential knowledge to help you better understand recording technology. For example, how sound is digitalized, or to troubleshoot or locate problem in a signal flow path when you hear weird noise in the recording. Sound is a form of wave. That means it transports energy from one place to another through a medium. When sound travels through air, it vibrates the air particles, and energy is transported from the sound source to your eardrum. Sound is longitudinal waves. That is, the back and forth motion of the air particles are in the same direction of travel of the sound wave. We'll first look at 7 waveform characteristics. On this graph, the x-axis is time. For the y-axis, you can see it in different ways. It sets here pressure and amplitude, but you can also see it as the distance travel of the air particle. So this air particle starts from its original position, moving towards one direction, reaches the maximum, then it changes direction, moving past the original position, then move to the opposite direction and come back to the original position. The maximum displacement for the original position is called amplitude. And the air particle has complete a cycle on this graph, and the time for the air particle to complete a cycle is called period. Velocity of sound in air is 343 meters per second. Speed of sound depends on the density of the medium. Temperature is also a factor because cooling a substance causes molecules to slow down and get slightly closer together, results in an increase in density. The frequency of sound is related to its wavelength by this equation, where v is the velocity of sound, f is the frequency, and lambda is the wavelength of the sound. Assuming v is constant, which is 344 meters per second if it travels through air, frequency and wavelength are inversely proportional. Phase specifies the location of a point within a wave cycle of a repetitive waveform. Two sound waves of the same frequency that are perfectly aligned have a phase difference of 0 and are said to be in phase. Two waves that are in phase add to produce a sound wave with an amplitude equal to the sum of the amplitudes of the two waves. If one of the two sound waves of the same frequency is shifted by 1/2 cycle relative to the other, the sound waves are said to be out of phase. Two waves that are out of phase exactly cancel each other when added together. The principle is used in noise-canceling headphones. When a piece of string vibrates, it vibrates at different modes. These are nodes, points where displacement is 0, and these are antinodes, points where the displacement is maximum. When a piece of string vibrates, these modes occur at the same time, therefore making sound of all these different frequencies. Harmonic partials, also known as overtones or harmonics, refer to simultaneous modes of vibration that begin with the fundamental note and continue as a sequence of tones that are integer multiples of that note. For example, 110 Hz, 220 Hz, 330 Hz, and 440 Hz, etc. The first partial is the fundamental frequency. Timbre is a general term for the distinguishable characteristics of a tone. It is mainly determined by the harmonic content of a sound and the dynamic characteristics of the sound. ANSI defines timbre as the attribute of an auditory sensation that allows it to be distinguished from other sounds at the same pitch and loudness. Another factor that could help us to distinguish sound from different instruments is envelope. Here's a demonstration of how the envelope of a sound affects our perception of the sound. I wrote this patch in Max to demonstrate sound properties. What are you about to hear is a pure sine tone with different envelopes. As you can see here, the first sound has a very fast attack and decay, a short sustain, and a fast release. It sounds like a percussion instrument. Now I change it to a longer decay. It should sound totally different from the first sound. It sounds more like a keyboard instrument. Then I change it to a slower attack and decay. Now it sounds more like a brass instrument. So except timbre, we recognize the instrument also by sound envelope, because the envelope of a sound tells us about how the vibration is stimulated. Using this patch, I can also show you how the waveform changes with the frequency and amplitude of a sound. This is the waveform of a 220 Hz sine tone. The amplitude increases with the volume. When I switch to an octave higher, that is 440 Hz, the wavelength is halved. Frequency is inversely proportional to the wavelength. The last thing to demonstrate is harmonics. So here I pick the fundamental of a note, and all the harmonics are calculated. You can hear clearly how the harmonics are added together if I turn it on one by one. If I play different notes now, you'll hear that as a timbre of one single note instead of a mixture of different frequencies. Now I turn off the even number harmonics. It changes the timbre of the sound. Adding more high frequency content to a note makes it sound brighter. When I turn it off one by one now, the timbre is getting more and more dull.